problem. So what we're doing here, this is very similar to that first problem from the video. We have a complicated looking rational integral, or an integral of a rational function that we're trying to compute. And our goal is simply to break it up into what we said in the pre-video was its partial fraction decomposition. In other words, here we have this common denominator of x minus 1 times x minus 4. And we can simplify this integral if we're able to break it up into something times x minus 1 plus something times x minus 4. And again, like that earlier problem, what's explicitly given here, we have the numerators are already given to us, this number 3 and this number 7. So we simply have to figure out which of those pieces goes in which of these boxes. And we can do this probably by, just sort of guess and check, or rather just sort of, trying one and seeing what happens. So if we try to put the x minus 1 over here, so it becomes 3 over x minus 1 and 7 over x minus 4, right? What we would end up getting, let's see if we can do this, right? Again, this is we have this common denominator idea. So this would have been breaking it up into two pieces, undoing the common denominator. To check and see if this is right, what we'd really want to do is recombine to get that common denominator. So we'd multiply this piece by x minus 1 over x minus 1. We'd multiply this piece over here, x minus 4 over x minus 4. And then what we see is we end up getting, let's see if we can do this. This first piece becomes a 3x minus 12, right? That's the 3 sort of distributing across the x minus 4. Plus, and then here we get the 7x minus 7, right? And that's the 7 distributing across the x minus 1. So we'd end up with all of that under, or rather over, x minus 4 times x minus 1. That's the common denominator that we were talking about. So here we did some guess and check. We guessed that the x minus 1 went under the 3, the x minus 4 went under the 7. We recombined to find this common denominator, and when the dust settles, what do we end up getting? Up here in the numerator, the x terms combine, right? So the 3x plus the 7x gives us the 10x. And then the constant terms combine. So the negative 12 and the negative 7 give us this negative 19 all over that common denominator. And then, right, this was sort of guess and check. So we made this guess, we multiplied, and now we go back to check, and we realize that this isn't quite right, right? That 10x minus 19 is not quite lining up with what we wanted up here. So in other words, the guess of putting the x minus 1 under the 3 and the x minus 4 under the 7 is probably not correct. Probably not correct. Which is a shame. Let's try the other way, right? So let's also guess putting the x minus 4 under the 3. So if we try to guess x minus 4 under the 3 and x minus 1 under the 7, what would we end up getting in this case? Right, well, we can play the same game if we try to find our common denominator. So here's us checking over here to confirm that this is right. We have 3 over x minus 4, and then we're going to multiply to get this common denominator. We'll multiply by x minus 1 times x minus 1, plus, over for the 7, right? We had 7 over x minus 1, and we'll just go ahead and multiply that by x minus 4 over x minus 4. Again, trying to get the common denominator of x minus 1 times x minus 4. Right, so let's go ahead and compute that really quickly. We should end up getting in the numerator 3x minus 3 plus 7x minus 28. All over that common x minus 4 times x minus 1. right? And this time we see when the dust settles, we can combine the x terms. We get 10x. We can combine the constant terms. We get negative 31. And that's exactly what we were hoping to get here. Right, so if we had this framework already given to us up above, sort of the knowledge that this would become 3 divided by x minus 3 divided by something plus 7 divided by something, just using some guess and check and trying to break up the denominator sort of from its common, sort of multiplication of terms into its separate pieces, we'd end up seeing that we can break it up in this way. And then the value of this, right? So the reason why we'd actually want to do this comes when we want to take the antiderivative of the original expression, the 10x minus 31 over x minus 1 times x minus 4. Because we realize now, let me actually zoom in so I can fit this in this box here. We realize that 10x minus 31 can now be rewritten as 3 over, I've already forgotten. I think 3 over x minus 4. I think the x minus 4 went there. Plus 1. No, it was a 7, wasn't it? 7 over x minus 1. Let's zoom out and confirm. Yeah, that's right. That's right. So we have the 3 over x minus 4. We have the 7 over x minus 1. And so we've just used algebra to break up this rational expression into smaller pieces, but the advantage is that these two new integrals are much simpler to compute. Specifically, we have this single x minus something in the denominator, and so each of these can be approached using the same u substitution trick, right? So for the first one, we can just say let u equal x minus 4. And then du, notice if u is equal to x minus 4, du just equals dx. Right, and then this integral, we still have a 3, but now we have a u in the denominator, and then the dx just became a single du. So the whole thing becomes 3 ln of u, which is just 3 ln of x minus 4. Right, you'll notice this is the exact same trick that we saw in the video as well. So this is a relatively common trick in the process of partial fractions. And similarly over here, we have the same game, let u equal x minus 1, let du equal the derivative of x minus 1, so that's just 1 dx. And then we end up getting the integral of 7 over u du, which just becomes 7 ln of u. Okay, so when the dust settles, and I'm gonna pause here for a second because I've been lecturing for far too long already. When the dust settles at this point, we end up seeing that we get the antiderivative of 3 over x minus 4 plus the antiderivative of 7 over x minus 1. So that just simplifies down to be 3 ln of x minus 4 plus 7 ln of x minus 1, and then plus that extra constant at the end, so plus c. All right, and let me pause there to see if there are any questions, comments, or concerns at the moment. All right, well, I have a question, sort of a rhetorical question. The big question in partial fractions is going to be, where do those numerators, that 3 and that 7, come from? Because if we scroll up, right, over the course of both of these problems, what we have is a lot of, sort of convoluted algebra trying to break up this rational expression into simpler expressions. And then once we can perform that algebra and verify that we can break it up like this, we can take the antiderivative of each of these pieces separately. And that's all well and good, but the biggest question is, suppose we're given an expression like this, right? So we have this, this just says compute this. I think we really want to say compute the antiderivative of x plus 14 over x plus 5 times x plus 2. We can recognize that because this denominator has these two pieces, the x plus 5 and the x plus 2, because it has these two pieces, we can go ahead and break this up into, its components. So it's going to be something over x plus 5 plus something over x plus 2. But at least at first glance, we're really unsure what the numerator should be. And here's where there's a big shift. In our previous problem, we had explicitly seen what these numerators were. But here there's no indication or no indicator of what the numerator should be. So we want to develop a strategy for figuring out what these numerators are, with the understanding that once we figure out what they are, the rest of the process will be similar to the problem we just saw. All right, and so here's what we're going to do. We are going to say, I don't know what these are, but I'm going to guess that they are some constants. And for the moment, I'm just going to call them the constant A and the constant B. So we end up saying that this is theoretically something we can break up into A over x plus 5 plus B over x plus 2. And now the question is, what is that? Like, what does that become? So we can actually play the same game that we did up above, but with these unknown constants A and B. So let's give this a try, right? To play the same game as above, I want to take this partial fraction decomposition and verify that it makes sense by finding the common denominator. In other words, on this side, I want to multiply by x plus 5 over x plus 5. And on this side over here, I want to multiply by x plus 2 over x plus 2. So I want to try to create and recombine these using a common denominator in an effort to figure out what A and B need to be. All right, so as I combine those, I'll end up getting that I have this denominator, right? This common denominator now of x plus 2 times x plus 5. And in the numerator, this A gets distributed across the x plus 2, right? So we end up with x times A. Maybe I'll write it actually as A times x. So the A gets distributed, we get AX plus 2A. Plus, let's move this a little bit. On the other hand, when we combine the other side, we end up with x times b. So we get bx plus 5b. Right? And all of this is over x plus 2 times x plus 5. And so I guess, why have we done this? We're trying to figure out what A and B should be. We know that when we rewrite this over a common denominator, it should equal this original piece right here, right? The x plus 14 over x plus 5 times x plus 2. So in the end, this should actually equal the thing that we were trying to integrate originally. So we end up seeing that this should all be equal to x plus 14 over x plus 2 times x plus 5. And if we have these two things being equal to each other, right? Notice we have our common denominator here is the same as our common denominator right there. So if these two things are equal to each other, the numerators have to be equal to other. And we end up with this equation involving the numerators, specifically ax plus 2a plus bx plus 5b equals x plus 14. All right. So again, lest we get lost in the algebra, I like to keep a big picture sort of understanding here. Our goal is to figure out an a and a b so that the partial fraction decomposition actually equals the original integral we were trying to compute. That means we need to choose an a and a b so that this expression will equal this expression, so that our thing involving a's and b's will equal x plus 14. And so to do that, we realize that this will only be true if our x terms, so ax and bx on the left-hand side, are equal to our x terms on the right-hand side. And simultaneously, if our non-x terms, our constant terms, so 2a and 5b, equal our non-x terms on the right-hand side. So in other words, we're going to break things up according to the x terms and according to the non-x terms. So according to the x terms, we've got ax plus bx equals x. And then according to the non-x terms, this is, what is that? That's 2a plus 5b equals 14. All right. And so at this point, we are now trying to solve for a and b, but we are really trying to solve these two equations, I guess, simultaneously. In other words, this is something that's called a system of equations, right? And we're trying to solve this system of equations for a and b to make these two equations simultaneously equal to each other. In this first equation, we can actually sort of ignore the x. We can factor out the x because there's just a single x in everything. So that first equation actually becomes a plus b equals 1, right? ax plus bx equals 1x. While the second equation, just remains the same. 2a plus 5b equals 14. Now our goal is to figure out a choice of A and a choice of B that simultaneously make these true. All right, and let's see if we can do that. My suggestion for doing these kind of equations, right, this system of equations, or to solve such a system of equations, there's a lot of different strategies possible. I'm going to recommend sort of writing them like this and then multiplying one of the terms or one of the lines to make some of the terms line up. In this case, we could multiply across the entire top. We could multiply by 2 to say that if a plus b equals 1, then 2a plus 2b equals 2. Right, so we end up with this new list of equations. 2a plus 2b equals 2. 2a plus 5b equals 14. And then we use this fact, we use these facts to figure out one of the equations. Specifically, in this case, we can subtract the second equation from the first to get 0a plus, I guess that's negative 3b equals negative 12. right? So again, my sort of trick for doing this was to try to eliminate one of the variables by multiplying one of the entire rows across by a single constant, in this case, multiplying it across by the number 2. That meant that I had a 2a in both equations, and then I just subtracted one from the other. So we end up with this expression, negative 3b equals negative 12. And so therefore, let's try that again. Negative 3b equals negative 12. Or in other words, b is equal to 4. And once we know b is equal to 4, we can double back and figure out what a had to be, right? If a plus b equaled 1, or if 2a plus 2b equaled 2, right? So a plus b equals 1. B is equal to 4, so a plus 4 equals 1. So a had to equal negative 3. All right, so this whole process over here on sort of the right-hand side of my screen, this process of solving this system of equations, in other words, of solving for a and b simultaneously to make sure that both of the original equations were satisfied, is an important sort of sub-skill here. We did some algebraic manipulation. We ended up figuring out that a and b had to satisfy this system of equations simultaneously. And then we were able to work all the way down and figure out that that was only the case if a was equal to negative 3 and b was equal to 4. So much fun. But what does that mean? What was the point of doing this, right? Well, if we go all the way back, we were trying to figure out a and b values to make these equations hold true. And so what that means, if we sort of take that information and go all the way down here, what that means is that the quantity x plus 14 over x plus 5 times x plus 2 is really nothing more than a over x plus 5. And now we know that a is equal to negative 3. So let me zoom way in here. Right, we know this is now negative 3 over x plus 5 plus b over x plus 2. And b we just said is equal to 4. So our purpose for doing this is that we can now rewrite our original integral as the sum of two simpler partial fraction integrals. We've broken up this larger fraction into these two smaller fractions. And we can solve this just like we did for the others, right? We will let u equal the denominator, x plus 2. We'll let u equal x plus 5. And we end up getting negative 3 ln of x plus 5 plus 4 ln of x plus 2. Let's see. Right, using the same u substitution trick as before. All right, and that was a lot. That was a lot of computation. Let's again pause, think about this. Let's see if we have any questions or comments or concerns at this point. All right. All right. So in this case, okay, oh, we do have a question. Why did we multiply the a plus b equals 1 by 2? Great question, great question. So let's circle back up here. So what we had here, we got to this point where we had these equations in which we had several things involving x's, some things not involving x's, and it all had to equal x plus 14. So the trick was to break this up into two equations depending on whether or not we had x's in it. And then we looked at this system of equations. The original system of equations, Gesundheit, was a plus b equals 1, 2a plus 5b equals 14. And at this point, our goal, our sort of stated goal, is to figure out what values of a and b work to solve these two equations simultaneously using, and I would say, any means necessary to figure out what a and b are. So there's a lot of different potential strategies for figuring out a and b. I illustrated one that I'm a personal fan of, but you might have your own favorite. And you can, of course, use that. I wanted to show one systematic way to get us all the way through. And the way that I showed, the way that I'm recommending is, there we go. The way that I'm recommending is to line these up sort of on top of each other as two equations and to try to align one of the columns to equal each other. So in this case, the reason that I multiplied everything through by 2 was to make sure that this 2a right here aligned with this 2a down here, right? And we can see that sort of explicitly right here, so that when it came time to actually, to move forward, I could subtract one line from the other, right? Subtracting this second row from this first row, and have all of my a's cancel out. So the goal here was, in essence, to have one of my variables, in this case, the variable a, cancel out and just be left with a single variable, in this case, left with b, so I can explicitly solve for b down here. So that was why we multiplied by 2's sort of across the board here. It was to try to get this a up top to cancel with the 2a that was below it. Again, depending on your comfort solving systems of equations, your mileage may vary. You might have a different strategy that you like to use. But I recommend this one as a systematic way that has the potential to scale to more complicated problems. Yeah, great question. Any other questions at the moment? Awesome. All right. So what I want to do, I want to keep an eye on the time here. I want to take a look at this problem 4, and I want to give you an opportunity to give it a try, to mess around with it. I will be doing it up here on the board nice and slowly if you all get stuck or want to double check, but I'm going to be quiet for a little bit and give you an opportunity to give it a try yourself. We're going to get at least as far as figuring out what a and b should be in this case. Okay, so take another 30 seconds or so to see if you can finish up or at least get to a sort of natural stopping point. I've hit, I think, my natural stopping point. I think I have an answer for A and B that I'd like to check with you all, confirm and see if it's what you got. I haven't gone all the way through to compute the rest of the integral, but I'm feeling like this is an appropriate point to pause and take a look. All right, so your mileage may vary, but briefly discussing what I have done here, I went ahead and I rewrote it as a over 3x minus 4 plus b over x plus 1. I then rewrote it over a common denominator, and in doing so, I got that it was equal to ax plus a plus 3bx minus 4b over the common denominator of x plus 1 times 3x minus 4. Again, that numerator I got by just distributing the a across the x plus 1 and the b across the 3x minus 4. So at this point, I had sort of, we do this process of we split it up into the two partial fractions, we recombine it to see what the new numerator will look like, and now this new numerator must secretly equal the old numerator from before, right? Because these are supposed to represent the same expression. So that new numerator involving a's and b's should equal x plus 15. And at this point, we can split it up into a system of equations, one of which is for the pieces out front of the x's. So ax plus 3bx equals 1x. And that's my blue equation here. And then for the green equation, my non-x pieces, that became a minus 4b equals 15. And then I used the same strategy as last time, only this time I noticed that we had a single a already isolated. So we had a 1a for blue, a 1a for green, and I went ahead and just subtracted one equation from the next. So blue equation minus green equation. Notice the a's cancel, so a minus a is 0a. 3b minus a negative 4b is equal to a positive 7b. And then 1 minus 15 equals negative 14. So we ended up at long last with the equation 7b equals negative 14. That would mean that b is equal to negative 2. And once we figured out what b was, I just thought, what do I have to get for a to have a plus negative 6 equal to 1? So I thought a had to be 7 as a result. So at this point, we haven't actually solved the original problem. I think it's easy to forget that, but we've done a lot of our heavy lifting. This is a lot of our crazy algebra nonsense, because at this point, we could go all the way back here. We could set up our new integral. We get the integral of, what was it, a over 3x minus 4, and a we said was 7. So this becomes 7 over 3x minus 4 plus, and then b we said was negative 2. Is that what we said? Yeah, a is 7, b is negative 2, so we'd end up with a negative 7 over x plus 1. And then we would have to compute these integrals using the appropriate u substitution again. So let me see. I'm trying to keep an eye on the time. With just about 12 minutes left, I'm going to leave the final computation of these using the correct u substitution. I'm going to leave that up to you all to do a little bit later. Right here, we would let u equal x plus 1. Here, we would let u equal 3x minus 4. And in both of these cases, we're getting a lot of mileage out of just letting u equal the denominator. One of the joys of breaking it up into these simpler fractions. All right, but rather than spend a lot of time working through the final details there, I want to pivot to problem 5, which introduces a really enjoyable, really challenging new wrinkle in this process. So our goal in this case is to calculate an antiderivative of 5x minus 2 over x plus 3 squared, where the denominator piece is being squared. And now, as we might sort of observe, this can be rewritten as 5x minus 2 over x plus 3 times x plus 3. And so we might hope to try to compute this using the same strategy as before, right? So we might hope to compute this by introducing an a over the one term, x plus 3, plus a b over the second term, x plus 3. But we run into trouble when we do that. And the trouble is sort of detailed in this equation right here. If we try to break this up into its partial fraction decomposition, we have an x plus 3, we have another x plus 3, so we would throw those in over here. Right? But the trouble is going to be as follows. If I try to take this piece and recombine it, right? We sort of do the same thing as we broke it up, we throw in the a and b, and then we recombine it to make a common denominator. Notice a and b, if we combine it, we end up with a times x plus 3 over x plus 3 times x plus 3 plus b times x plus 3 over x plus 3 times x plus 3. So this is the exact same process that we did before. If everything was going smoothly, we could now take this and compare it back to this, and then compare their numerators. But something actually kind of breaks down here. Something breaks down here. And the trouble is that if we take a look at our numerator, we end up getting a system of equations that doesn't work. So if we just if we just follow our nose, we end up getting that our numerator system of equations is ax plus 3a plus bx plus 3b equals 5x minus 2. And this just won't work. We end up seeing, on the one hand, that a plus b equals 5. That's our blue equation. And on the green hand, right, on the green equation, we'd end up seeing 3a plus 3b equals -2. And there's no way that both of those equations can sort of exist simultaneously, right? Or that we can satisfy both of those equations simultaneously. So again, those equations, we ended up with a plus b equals 5. That was in blue. And 3a plus 3b equals -2. That was here in green. So what happened, right? This completely broke down in this case. What happened here? Well, if we think back to our original goal, right? Our original goal was to break this up into a potential partial fraction decomposition. In this case, a over x plus 3 plus b over x plus 3. We would then recombine them to find a common denominator. That common denominator would align with our original common denominator. And then we would go on to solve for a and b in the numerators. The trouble here is that this original expression in red, right? I mean, this expression right here, this is already in the form of a common denominator, right? The x plus 3 and the x plus 3 already have a common denominator. So there's no need to do this recombining like we did over here. In fact, we could just add the numerators right away. So we'd end up with a plus b over x plus 3. And now there's no guarantee that this expression over here can be rewritten into this expression over here. In other words, as we try to break this up across the partial fraction a over x plus 3 plus b over x plus 3, there is no way to do it because x plus 3 already was our common denominator. So that kind of sucks. That's a bummer. Our strategy from before no longer works. So what can we do instead? So if we cannot express these things in the form a over x plus 3 plus b over x plus 3, we can attempt to break it down in a different way, right? Under a different set of partial fractions. And in fact, the recommended strategy is to, again, include an a over x plus 3. That's what we have right here. But instead of having a b over x plus 3, we have a b over x plus 3 squared. So we include this piece squared. So it's no longer a nice linear factor. It's no longer like an x plus something or an x minus something. We've added a little bit of extra complexity to this one denominator. But hopefully, we can break up this new denominator, or I should say we can break up these new partial fractions appropriately. And it turns out that that is the case. We can do this. So if we have a squared term in the denominator, we have to use this extra little trick. But the end result is as follows. We end up, well, let's see what we can do. As far as finding our constants a and b, we have already a over x plus 3 plus b over x plus 3 squared. So we break it up into a potential partial fraction, and then we try to rewrite it under a common denominator to get it equal to the original 5x minus 2 over x plus 3 squared. So we can do this straight up by multiplying the a by an additional x plus 3 and just leaving the b alone, right? The b already has the correct denominator, so we're actually okay there. And so with this multiplication, we can actually simplify this. So we end up with an ax plus 3a over x plus 3 squared plus a b, where the b is left alone, over x plus 3 squared. And that ends up simplifying down to be our numerator, right? We end up with a, what, ax plus 3a plus b. And that should equal the numerator from before, so the 5x minus 2. And in fact, if we play the same game as before, we see that this is actually something we can compute in a relatively straightforward manner. If we take our ax, if we match our x's, I should say, right? So our blue equation, that we just get ax equals 5x. And so that gives us a equals 5 straight up. While with our green equation, we end up with 3a plus b equals negative 2. And so if 3a plus b equals negative 2, and a is already 5, we get 15 plus b equals negative 2. And so b is going to equal negative 17. And we are once again good to go here. Right, so our final integral here, it would simplify down. We already have so our a is 5. We'd end up with a 5 over x plus 3. And then our b, we'd end up with sort of gross looking negative 17 over x plus 3 squared. And keeping an eye, we have about 2 minutes left. I'll go ahead and finish this problem. Notice that over here, Well, for this first one, it would be exactly the same as we've been seeing before. We can let u equal x plus 3. This becomes the integral of 5 over u. So that becomes the integral of, or that becomes 5 ln of u. So that becomes 5 ln of x plus 3. Over here, I also recommend letting u equal x plus 3. We'd get du equals dx. And the whole thing would become the integral of negative 17 over u squared du. Right, the only difference here is that instead of jumping immediately to the ln, as we've probably gotten used to for these kind of problems, here we'd end up with, this is the integral of negative 17 u to the negative 2, which is just a negative 17, right? Not ln, Gesundheit, not ln, but this becomes a u to the negative 1 divided by negative 1. Which we can rewrite as positive 17 over x plus 3. So when all of the dust settles, right, our final answer here, we'd get 5 ln of x plus 3 plus 17 over x plus 3. Let's see. Right, so we get this added wrinkle, or this added sort of challenge when it comes to compute something where the denominator term is not just a linear term, but in this case was an x plus 3 squared, or an x plus 3 times x plus 3. But the overall sort of strategy of breaking it up into potential partial fractions with unknown numerators, and then computing those numerators through a variety of tricks and algebraic nonsense is all the same here. Okay. So to summarize, this sort of partial fraction, this was our last new integration technique. It's definitely our most algebraically annoying or frustrating or time consuming. It involves a lot of sort of finicky algebraic manipulation in solving these systems of equations, but it's good fun and we can do it. That's not a great takeaway message, but that's what I've got for the moment. Yeah, with that, have an absolutely wonderful rest of your Monday. You know, I'm trying to get better at letting you all go by row. So if you're in the first row and you're ready to go, you can take off. Try to stay dry today, stay healthy. It was great to see you all again. I'm excited to be back in class with you. Take care and we'll chat soon.